All right, let's talk about double displacement reactions. Double displacement reactions occur when cations of two different salts swap the anion and cation with which they're associated. For the reaction to occur, there needs to be some sort of driving force, whether it's a precipitate or a gas evolved or a weak or non-electrolyte. Something like that has to occur. Remember, a precipitate is an insoluble solid that forms and falls out of solution. That's where our water solubility rules are going to come in. If you're unsure of those, go back and look at that video. And it should be in the same playlist. The evolution of a gas, that means it's going to bubble, it's going to fizz, or gas is going to escape the solution in bulk and be dispersed into the atmosphere at large. So the general rule is that AB plus CD is going to go to AD plus CB. That is, the cation and the ion are going to swap partners. Several types of those that are common. You can get an acid-base neutralization. We've talked about those a little bit when we talked about titrations and things. But the acid is going to react with the base, which is a metal hydroxide, to produce a salt and water. We can form an insoluble precipitate. That is, two soluble salts react, and then I get one salt that's insoluble and falls out of solution, and then the soluble salt remains in solution. Or we can get the formation of a gas. An acid can react with a sulfide salt to produce a salt and hydrogen sulfide gas. Now, you can form a gas directly like that, or you can form it indirectly. There's a couple of different ways that you can do that we're going to talk about. Double displacements sometimes form compounds that are unstable. So essentially, you get a double displacement followed by a decomposition. We call that an indirect formation of a gas. Carbonates and bicarbonates will react with an acid to produce carbonic acid, H2CO3, but that compound tends to be unstable, and so you'll form carbon dioxide and water, and you'll get bubbling and fizzing of carbon dioxide escaping the solution at large. And the other one, sulfites and bisulfites, react very similarly, except you form H2SO3 into the H2CO3, and so you end up forming SO2 and H2O. So the sulfite or bisulfite salt with a non-oxidizing acid is going to produce a salt, sulfur dioxide, and water. Sulfur dioxide has a very distinct odor, smells like burning tires. And it's because those burning tires they're vulcanized, meaning they've got sulfur in there to strengthen the rubber, and when you burn it, you produce sulfur dioxide. So it's a very similar smell. Ammonium salts, if you add a base to them, will also produce it. Now, ammonia doesn't bubble out of solution like CO2 does, but it will escape, and it does have a characteristic ammonia smell that you can tell that you've made it. But the double displacement product is ammonium hydroxide. Turns out that's unstable and falls apart to form ammonia and water. So your resulting solution will be somewhat alkaline because of the ammonia. So ammonium salt, metal hydroxide salt, you're going to get a salt where it's from the metal of the hydroxide, the anion of the ammonium salt, and then you're going to get ammonia and water. So we're going to write several of these double displacement reactions, and we'll work on writing the net ionic and net ionic equations of each. Okay, so let's write the reaction for these and then include the ionic and net ionic, and that'll be a practice of what we did earlier. So double displacement, hydrogen's going to go with hydroxide to form water. So it's going to form water, and then a salt of what's left over, sodium and chloride. The cation comes first. NaCl, +1, -1. Sodium chloride is a water-soluble salt, so we're going to write AQ. Now to write the ionic, what doesn't split up? This is my non-electrolyte. Everything else splits up. This reaction's already balanced as is, so we're going to write H plus AQ plus Cl minus AQ plus Na AQ plus OH minus AQ, water, liquid, plus Na plus AQ plus Cl minus AQ. So where are my spectator ions? The sodium and the chloride. That should have been a plus. And so then our net ionic is going to be H plus AQ plus OH minus AQ is going to form some water. So that's my net ionic equation. That's an acid-base neutralization. So now if we look at the barium chloride and the silver nitrate, the barium's going to go with the nitrate. So we're going to say barium BaNO3. Barium's in group 2A, so plus 2, minus 1 for the nitrate. So BaNO3, 2. Nitrates are water soluble, so that's AQ. The silver is going to go with the chloride. So we're going to write Ag and Cl. Notice I did not drag that over. Don't pull over the subscripts except for in the polyatomic ions. Silver tends to be plus 1. It's a transition metal. Chloride's minus 1, so that's fine. But silver chloride, chlorides are usually soluble, but silver's an exception, so that is your solid. And when I write solid, that indicates that is the precipitate. And so to balance it, that's going to have to be a 2 there, and we're going to put a 2 there. Now let's split it apart. This is the thing I'm not going to split. It's the insoluble salt. So we're going to write Ba2 plus aqueous plus 2 chloride minus aqueous. Notice the 2 comes out front, plus 2 Ag plus aqueous plus 2 NO3 minus aqueous, going to form Ba2 plus aqueous plus 2 nitrates aqueous plus our 2 AgCl solids. The barium and the nitrate are your spectator ions. And so then we got 2Cl minus AQ plus 2Ag plus AQ, forming 2AgCl solids. Now there wasn't a factor that we needed to reduce out until we canceled out the spectator ions, but you're going to get rid of all those 2's for your final answer. So to speak, chloride plus silver ion goes to form silver chloride solid. It'd be in your final answer. Okay, direct formation of a gas. You're going to form the zinc with the chlorine, so ZnCl. That's plus 2, transition metal, minus 1, so ZnCl2. Chlorides are usually soluble. Zinc is not an exception. Then we said if we rated acid with a sulfide-containing salt, it would be H2S. That stinks to high heaven. Smells like rotten eggs. But we're going to need to put a 2 there to balance the chloride and the hydrogen, and then that gives us a balanced reaction. This is our thing. Since it's a gas, it's not going to split up. Split up everything else. So 2H plus aqueous plus 2Cl minus aqueous plus Zn2 plus aqueous plus sulfide 2 minus aqueous. Now, this is initially listed as a solid. It's not water soluble, so really we shouldn't split that. We should call it ZnS solid. This is the case where you don't split something because it's so doing this would be wrong. And a lot of times you only see a precipitate on the product side, but if the thing is not water soluble but reacts, I wouldn't split it. And so we're going to continue. And so Zn2 plus aqueous plus 2 chloride minus aqueous plus H2S gas. And so I don't split that. So what is left to cancel? Since this did not split, and this is, so since that's solid, that's not a water soluble salt, so I can't split it. And so A lot of times you don't see those on the react side, but you do occasionally. And if you split it, you're wrong. And I kind of did that to show you how people mess it up, but you really wouldn't split that. So when you get your net ionic, you only cross out the chloride. So we're going to say 2H plus aqueous plus Zn solid. So zinc sulfide solid forming zinc ion plus H2S gas. Now, you do occasionally get something like that when you have something that's not soluble on the reactant side, or you've got a weak electrolyte on the reactant side. You need to be careful. Now, these next ones refer to the indirect formation of a gas. And so we're going to form it indirectly. So let's just do the double displacement. Sodium's going to go with chloride, so you're going to get NaCl, like always. That's water-soluble salt. But then hydrogens go with the carbonate. That's a -2. That's a +1. So you would form H2CO3, aqueous. Now, just like in the previous problem, that's not where you want to leave it. So we're going to, don't want to form that. What I want to form is CO2 gas plus H2O liquid. And then you can balance accordingly. So we're going to need 2 of those and 2 of those to balance out the reaction. If you have to write it out like that and then break it apart, that's fine. If you can just go straight for what actually forms, certainly be my guest. I'm doing it here for an illustration. So what doesn't split up? The CO2 and the water. Those are both covalent compounds. So we got 2Na plus aqueous plus CO3 2 minus aqueous plus 2H plus aqueous plus 2Cl minus aqueous reacts to form 2Na plus aqueous plus 2Cl minus aqueous plus CO2 gas plus H2O liquid. Now, spectator ions are in the salt. So all that's going to go away. And so what we're going to be left with is carbonate, CO3 2 minus aqueous plus 2H plus aqueous reacting to form CO2 gas plus H2O liquid. And that's the essence of what's going on. What's really going on when those two react? The carbonate and the acid are reacting. The sodium and the chloride are just kind of hanging out, which is why they're spectator ions. You get a very similar situation in the case of the sodium sulfite reacting with the HCl. You're still going to get NaCl, but you're going to get H2SO3 aqueous, which, yes, that's right, SO2 gas plus H2O liquid. And then it's going to balance pretty much the same way, because all I did is replace the C with an S. And so the ionic and net ionics will look pretty much the same. 2Na plus aqueous plus SO3 2 minus aqueous plus 2H plus aqueous plus 2Cl minus aqueous for 2Na plus aqueous plus 2Cl minus aqueous plus SO2 gas plus H2O liquid. Again, the sodium and the chloride cancel out. So we're left with sulfite, SO3 2 minus aqueous plus 2H plus aqueous forming SO2 gas plus H2O liquid. So looking at this last one, we're going to swap these ions just like before, and we'll get sodium with chloride again, and we'll get ammonium ion with hydroxide. Everything's +1 or -1, so the formulas work out. But again, I don't want to form this one. It's going to be ammonia NH3 gas plus H2O liquid. Ammonia is going to have a distinctive odor. Now when I form my ions, we're going to get NH4 plus aqueous plus Cl minus aqueous plus Na plus aqueous plus OH minus aqueous plus reacts to form Na plus aqueous plus Cl minus aqueous plus NH3 gas plus H2O liquid. Now canceling out the ions, it'll be the ions in the salt again. And so we're going to get ammonium ion aqueous plus hydroxide aqueous, going to form ammonia gas and water liquid, and that would be our net ionic equation. Okay, so let's identify these now that we've gone over all the types: combination, decomposition, single replacement, double displacement, or combustion. That first one, C3H8 plus 5O2 forming CO2 and H2O, that's one of the combustion reactions we actually balance. So hey, that's a combustion. Here we got, next we got ammonium dichromate, one compound breaking apart into several different elements and smaller compounds. So hey, that must be a decomposition for B. C, we've got sodium metal reacting with water to form sodium hydroxide and hydrogen gas. Hey, that's an alkali metal reacting with water. That was a single replacement. The sodium's replacing the hydrogen in the water. Here we got two ionic compounds reacting together, sodium chloride, lead nitrate, and they're swapping partners there, cation and anion. So that must be a double displacement, in this case, a precipitation. E, you've got magnesium oxide plus CO2 forming magnesium carbonate. So I've got two compounds reacting to form one compound, so that must be a combination.